build off of that heat discussion that we had in the previous video, and we're going to talk about heating curves. So heating curves show boiling melting points in the amount of heat needed to change state in a certain substance. And so they outline where things start to melt, where they start to boil, and then how easily you can add energy, or I guess not necessarily add energy, but how easily you can raise the temperature based on the slope of the graph. So, heating curve of water, that's what's being shown in this heating curve. What you should see is this first part of the curve is that's the melting point. Okay, and that occurs at 0 degrees Celsius. Okay, water melts at 0 degrees Celsius. We know that. It also freezes at 0 degrees Celsius. Okay, and then its boiling condensing point, okay, is at 100 degrees Celsius. So that's the second flat point. And what you can see is you need to absorb far more heat, much more energy to boil something than you do to melt something. And that makes sense, right? Because we're needing to break the attractive bits or the attractive forces between the individual particles in water. Okay? Now, to calculate the energy to change a state or phase, we're going to use what's called the heat of fusion and the heat of vaporization. The heat of fusion is the energy needed to change from a solid to a liquid. And so that is going to be equal to Q, or I guess the heat needed is going to be equal to the mass times this constant, this heat of fusion constant. And same thing for heat of vaporization. You're going to use mass times this vaporization constant, which you will get. So for practice, we need to calculate the amount of heat needed in joules to warm 50 grams of ice from -3 degrees Celsius to 110 degrees Celsius. And so what I want to talk you through is the fact that this is quite a few steps. We can't just use Q equals mc delta T once, going from -3 to 110, because this water is in 3 different states in each of these. Okay, and so we have multiple steps. So our first step that we need to figure out is Q going from -3 Celsius to 0 Celsius. Okay, and then we need to find Q for the melting bit. Okay, because that's going to stay at 0 degrees Celsius. There's not going to be any sort of temperature change. Our third step, okay, we're going to go from 0 to 100 Celsius, right? Because that's where we're going to hit our boiling point. And then it's not going to change temperature. It's going to stay at 100 degrees as it's boiling or vaporizing. And then finally, what we can do is we have the gas going from 100 degrees Celsius to 110. Okay, so there's 5 steps here that we're going to go through. And I will outline each one of those for you. Okay? So our first step, we're going to use Q equals mc delta T to figure this out. Okay? So we need to use the specific heat for ice, right? Because this is ice going from -3 to 0. And so we have 50, okay, times the specific heat for ice times the temperature change. That's a +3, okay? Final minus initial gives us a +3. So we're sitting at 316.2 joules. Second step, we're going to calculate melting. For that, we're going to use that equation where we have mass times LF. So we have 50 times 340. That gives us 17,000 joules. Okay? Then, for our third step, we're going to do water from 100, or from 0 to 100. So Q equals MC delta T again. 50 times 4.184, because now we have liquid water, so we're going to use liquid water, times 100. We've got 20,920 joules. Evaporating, boiling, vaporizing, we're going to use LV. That should be LV, not LF. Okay, so 50 times this 2270. So 113,500 joules. It's quite a bit of energy that we have pumping along here. And now, last step, water vapor from 100 degrees Celsius to 110. Q equals MC delta T again. We have 50 times 1.996 times 10 for 998 joules. And we're not done yet, because those steps we did all separately. We've got to add them all up. So if we add them all up to total up exactly the amount of heat that was needed to warm that 50 grams of ice from -3 degrees Celsius to 110 degrees Celsius, we're going to add all of these up. And that gets you to 152,732.2 joules. I would round up and say it's roughly 153 kilojoules. Quite a bit of energy needs to be absorbed to do that. And you should know that if we were able to, we do a heating curve lab where you would literally warm ice up from whatever the ice was sitting at all the way up to 10 degrees above boiling. It would be really, really boring for you guys, but you would see just how long it is and how much you have to pump heat into it using a hot plate. Okay, that is it for today. You should have some heating curves practice, and then you can check it using the key that should be up front. Thank you.